Okay, so let's talk about the normal distribution. I think I could finish this today. Okay, so listen, when we have what is called normal distribution, this doesn't have anything to do with somebody, being liked or being conforming or whatever, right? Like that's not what normal means. Normal is basically, it's the way a distribution looks, right? And it's a continuous probability distribution. Now, what does the normal distribution look like? The graph of it is bell-shaped and it's symmetric to the mean. The mean, median, and mode are all equal. And they are located at the center. There's a little bit of a repeat there. The curve is continuous. Okay, here it approaches but never touches the x-axis. And then the total area under the curve is equal to 1 or 100%. So basically the entire curve represents 100% of your population. Okay?
So there's no like outliers.
Well, all of them included. Okay?
So like it's like not when you take out the lowest and highest.
Right. Okay. So here's how a normal distribution would look like. So look at this one. You have n equals 100, right? 100 people took a test, and then you looked at their, you made a histogram, and this is what the histogram looks like. Now look, if you were to sort of, put a curve on this, do you see how it looks? Right? Do you see how the mean and the median are in the middle? The mean, mode, and median are in the middle. Are in the middle, and then this is symmetric around the mean and the median. It's close. So now this is n equals 100, right? This is n equals 100. In order for you to become absolutely precise, you now need to increase your n. This is why when you're gonna do a political poll, let's say, it doesn't make sense to ask 100 people, right? Now, if we increase to n equals 1,000, look at how much more smooth that curve becomes. And look at this one here. The mean and the median are right here, right? And the curve is symmetric around both of them. And now look, when you increase to n equals 10,000, look at how that looks now, right? And then as you increase to n equals the population, millions, look at how smooth the normal curve looks. So this is what a normal distribution looks like, all right? It's a bell-shaped curve. The mean is exactly at the center. Mean at center. Median at center. Okay? That's super, super important. Okay? So, I'm just going to throw out a random number here. For example, okay, suppose there is a poll and you get the results and you find out that the mean is 55. The median, the one that is exactly in the middle, is 55. Okay? And guess what? The mode, the number that occurs most often, is 55. That is a perfect normal distribution. All right? Now, do you remember what standard deviation was? Yeah. Standard deviation is basically a measure of how much the values differ from the average, from the mean. All right? So, for example, suppose you have a set of scores, and the average, the mean, is 85. Okay? Now suppose standard deviation is 5. All right? What does that mean? Here is 85. Okay? Most people got between 80 and 90. Okay? So the standard deviation is 5. So if you go 5 away from the average, you're at 80 or 90. If that's the standard deviation, it means most of the scores fell within an 80 or a 90. Okay? So let's look at some things here. Values that are close together have a small standard deviation. So if everybody got like, in the 80s, then there is a very small distribution because most of the people got very close to the average. Standard deviation has the same units of measurement as the original data. So if it's test scores and it's percent, then it's percent. Okay, this is important. Here. For many data sets, a value is considered unusual if it differs from the mean by more than 2 standard deviations. All right?
I keep breaking my pencil.
So a value is considered unusual if it's more than 2 standard deviations. So look at this one. If the average is 85 and the standard deviation is 5, all right, now if I'm going like to the left, down, what's 1 standard deviation away? 80. What's another standard deviation away? 75. That's 2 standard deviations away, the 75. Anything past that is considered an unusual score, okay? So if you think about like heights, right? What's usual for this population in this region of the town, right? Anybody who is 2 standard deviations away is considered to have, let's say, average, unusual height. Or like if you are talking about like rainfall, okay? For a given part of the world, what is the average amount of rainfall for May?
7.
Right? And then if you get something that's 2 standard deviations away, then that's average amounts, unusual amounts of rainfall.
Is that what outliers are?
Yeah, outliers will be unusual, will be considered unusual. So we compare standard deviations of 2 different data sets only if they use the same scale and if they have the same units, right? So be careful about that. So like if you're comparing heights from people in France and the US, make sure everything is in meters or feet, right? You have to make sure that everything is on equal footing. Okay, let's go on to some of the good stuff. The shape and position of the normal distribution depends on mean and standard deviation, all right? So take a look at this one. You have 2 normal, both of these, the red and the blue, are considered a normal distribution, okay? The standard deviation for the blue one is less, okay? So the blue one has smaller standard deviation. The red one has a larger standard deviation. What do you notice? For a larger standard deviation, how does the curve look?
Smaller.
It's shorter and it's flatter, right? So the curve is flatter. Does that make sense to you? Take a look at the blue. It's got small standard deviation. This dotted line is the average. If it's got small standard deviation, all of the data values are very close to the average and they all pile up here. If it's got high standard deviation like the red, the data values are more spread out, so it's flatter, it's wider. Isn't that cool? So now, take a look at this one. Suppose the mean of the data changes. Suppose the mean of the data changes. So, a couple people took, a lot of people took the test, and then there were maybe like 20 people who were absent, and then they took the test later, and they changed the mean. So, yeah.
Shift left or right.
It shifts left or right, right? If the mean shifts, but the standard deviation, look, the standard deviation is the same, so the graphs have the same shape. But the average changed, so the graph shifts horizontally. Does that make sense?
Yes.
It does, right? I can't spell horizontally, apparently. Okay? Now for the good one. Now for the empirical rule. Okay, so this rule has two names. It's either called the empirical rule, or it's called the 68, 95, 99.7 rule.
Yeah.
Huh?
I'm gonna go with 68.
No.
Okay, so it turns out you really have to know both. You've got to know the numbers. Okay, so here's how this works. This is where the numbers come from. If you have a normal distribution with a bell-shaped curve, right, then about 68% of all the data values fall within one standard deviation of the mean. This is the big idea. This is the big deal now. Here, the red line is the mean, okay? 68% of the data points lie within one standard deviation to the left and one standard deviation to the right, okay? So if we wanted to do an example, suppose there is a test, okay? The average is, what do you want to make? Let's make it 85 again, okay? So that's the average, 85. And suppose, to be consistent, our sigma is 5%. So this lower number is 80 and this is 90, right? Now, if 100 people, if 100 students took the test, 68 of them are within this region, all right? So let's say only 10 students took the test. How many people would you say fall within this range? 6.8, so 6 to 7, right? That's why, so you can't have 6.7 people. That's why it says it's about 68%. So either 6 or 7 students will have grades between an 80 and a 90. Well, that's the thing. Well, it's people, like, there could be one more or one less, right? Especially when you're talking about 10 students, like, it's not going to be, like, exactly. Okay, so that's 68%. Now, if we widen the pot, the mark, so this is, so our standard deviation was 80. I'm sorry, the mean was 80. And so one standard deviation, no, this was 85. Sorry. One standard deviation went from 80 to 90. Now, if I go to 2 standard deviations, that's 75 and 95, right? In that region, 95% of all the values will be found. All right? So 68% was within one standard deviation. Now, if you widen it, that's 95% of your scores. All right? They will fall within 2 standard deviations. Okay? So the whole thing, though, happens symmetrically. So here's how it all works. It's 68% here, right? So it's 34 and 34. 95% total. So what's the difference between 68 and 95? How much difference is there? 27. Of that 27, you split it in half. So 13.5% is here and 13.5% is there. Now, if I go one more standard deviation out, okay, 3 standard deviations, then I get 99.7% of the data. All right? So hence the rule 68, 95, 99.7. Okay? And so I have 2.4% there and 2.4% there. All right? Okay. So let's do some examples. Here's one on IQ scores. IQ scores have a bell-shaped distribution. No, you'll see right now. Depending on the problem, you might have to do a little sketch for yourself. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. Okay, so X bar is 100, sigma is 15. What percentage of IQ scores are between 70 and 130?
99.7.
Right. Let's see. So what we're going to do is draw that bell-shaped curve here. Okay? Let's put the mean first. That's x bar equal 100. Standard deviation is how much? 15. So here, that's 85 and 115. But I need to go a little bit more, right? So I need to go one more. 70, 130. How many standard deviations did I go? 2. So that's 2 standard deviations. That's 95%. So it's 95% of scores. Okay? So you've got to know the numbers. 68, 97, 95. I'm sorry, 68, 95, 99.7 in order to go from there. All right, so let's take another one. The heights of 880 students at East High School are normally distributed, right? Normally distributed, that's what it means. It means it's got a normal distribution. Mean of 67 and a standard deviation of 2.5. About how many students are more than 72 inches tall? All right, so yeah. Okay, so let's see how we do it. Let's draw this thing again so we can see it, right? Here's the distribution. Where is the mean? 67. And then it's 2.5%, and I need to go to 72 inches tall. So how many standard deviations? One standard deviation is 69.5. Another standard deviation is 72%, right? Okay, so now, and then I have the counterparts there. So 64.5, 62%. Okay, so here, that's 2 standard deviations. So that much of it in the middle is how many percent? What percent is the 2 standard deviations? 95. 95%. So now what I want is the students that are more than 72 inches tall, that's here. Okay, if that's 95%, how many percent are outside? 5. But I only want half of it. I only want the half to the right, right? So this is only 2.5%. So you do 880 times 0.025 because it's 2.5%. Right, let me write that. 880 times 2.5%. And that is 22. So we say 22 students are more than 72 inches tall. Okay, now it says what percent are between 59.5 and 69.5. So where is 59.5? 59.5 is right here. And 69.5. So now I have to add, look, this is 1 standard deviation away, and it was 68%. So it was 34, 34. Oh, no, wait, sorry. Sorry. This whole thing was 95, right? So look, it's like this. 34, 34, right? And then how much were these? 13.5, 13.5, right? So that whole thing is 95. And then how much is here? 2.5. So that's 95. I'm sorry, I wasn't reading properly. Until here. So which ones am I going to take? From 59.5 to 69.5. So I'm going to take this, 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 and this. Okay? So 2.5, 13.5, 34, and 34. 83.9%. So do you see how like the point is to break it down into compartments. Okay, next is z-score. Z-score is another way to measure like normalcy of values, right? Or how usual a value is. So the z-score is important to compare the location of data values within the data set. That's how it's used, right? So you don't compare it to people like in another data set, within the data set. Is this person like close to the mean, away from the mean, and so on. Okay, z-score is the number of standard deviations that a given value is above or below the mean. All right, so now we're going backwards. Suppose I tell you this one person's height is whatever, 70. You can tell me how many standard deviations away from the mean it is. All right, so here's how you calculate z-score. X minus x bar over sigma, and then it's necessary to round to 2 decimal places. So the first few are just basically plugging things in. So you need to find z. X is 24, x bar is 29, and so on. So z, we said, is x minus x bar over sigma. And this is 24 minus 29 over 4.2. Z is negative 1.19. Okay, a few things here. Order matters because if you get a negative value, it tells you you're below the mean. If you get a positive value, it tells you you're above the mean. So the fact that you have a negative means the value is 1.19 standard deviations below the mean. What does that mean? Let's take a look at what that means. Here is the normal curve, and here's x bar. Okay? 1 standard deviation, 2 standard deviations. Your score is somewhere here. Okay? That's what that means, right? So you can see how, usual or unusual that specific value is. Okay, so here you need to find x. Let's go ahead and find x. I have z, x bar, and sigma. So again, z is x minus x bar over sigma. Z is negative 1.73. That's equal to x minus 48 over 2.3. What do I do now? So I get negative 3.979 equals x minus 48. Add 48. X is 44.021. All right, so look at this one. So there is a comparison of two individual data values, and we're going to try to determine which is more extreme. All right. One case is a 72-inch height of a man, or 237.1 pound weight of the man. All right, so we're going to see which one of these values is more extreme. We obviously can't compare the two values directly, right? Because you can't compare weight to height. So we have to look at how usual the one value is, and then how usual the other value is, and see which one is the extreme one. All right, so what we have to do is we have to compare using their z-scores, right? And so what are we going to compare it against? Well, here is like a sample result. For men, heights have a mean of this many inches and standard deviation of this, and then the weights have a mean and standard deviation here. So we're going to find height and weight z-score separately. So let's do the height first. All right. The z-score for the height is going to be x minus x bar over sigma. So 76.2 minus, what's x bar? 68.34 over 3.02. Now, you have to make sure that, look, so like this is inches, right? They're all inches. So how much is z-score here? $2.60, right? Two decimal places. 2.60. So that's 2 standard deviations away, right? And is he taller than most people or shorter than most people? Taller, because it's a positive standard z-score. What about for the weight? It's going to be 237. Not 3 inches. He's, so the standard deviation is 3, right? He's 2.6 standard deviations away. So 3, and then another like 1.5. So he's like 7.5 inches taller than most people. He's pretty tall. So how about the z-score for the weight? 2.45. So is his weight more extreme or is his height more extreme? His height is more extreme. So, all right, so to do this with the TI Inspire, all right, so what we want is, it wants the z-score, the interval of z values for the middle 50% of the data. All right, so let's just draw that for a minute and let me show you what we're looking at. Here's the middle 50%, right? Okay, that means this and this are 25% and 25%. Is that right? So that means this is the 25% mark, right? And then you go 50 more, and this is the 0.75% mark. You want to do only because it's 50%. If it wasn't 50%, then it wouldn't be. So now what you do is go here in Add Calculator. What you're going to do is menu.
Wait, where are we? Are we going?
Just in a calculator, yeah. Menu, statistics, distributions, inverse normal. All right, I'll write that down right now. So menu, statistics, inverse normal. No. The area, okay, so the area, no. First, it's going to be 0.25, the bottom value, and it's negative 0.67. So I go here. I'll tell you. That's the z-score, negative 0.67. Now you say less than or equal to z less than or equal to. Now you have to go back to your calculator. Bring this back so you can edit it, so you don't have to go back to the whole thing. Now here, remember we put 0.25, that was the left end point. Now we're going to put 0.75, that's the right end point, and we get 0.67. Now it's symmetric because it's, 50%. So it's 0.67. That means it's the z-score here, it's 0.67 standard deviations to the left, 0.67 standard deviations to the right. Now let's do part B, which is the outside 20% of the data. Let's draw for that. If I want the outside 20%, how much is the inside? 80%. That means 80%. That means this is 10 and this is 90. So figure out the left one and then go, okay, 10 plus 80 is 90. So now I go here, right? Bring this back, and I'm going to put 10. Negative 1.28 less than or equal to z less than or equal to 1.28.
Unless it's a problem that asks
unless
like two different ones.
Exactly. All right. So that's that. Go ahead and do the homework for tomorrow. For next.